Thank you very much. So this is Metamorphic Fuzzing for C++ software libraries. This was my PhD thesis, and this is joint work with my supervisor at the time, Ali Donaldson, and Tobias Grosser and Thorsten Höfler from your group. So for a motivating example, let's say we write an amazing new arbitrary precision arithmetic library, but someday someone comes to us and gives us this bunch of code, and they're like, this doesn't work. We spent a lot of time trying to debug it. Could you please help us and see where the problem lies? So you go ahead and this is using your library. You go ahead and try to understand where the problem is, spend a couple of hours, maybe even a couple of days, reduce it to a minimal example, and then actually taking out a piece of pen and paper now that they can actually follow what's happening in this code, you realize that your library sees this as true and it's supposed to be false. So this whole bunch of code simplified into this expression, but wasting lots of people's times to even find out the root cause, and then even more time to actually fix the issue. So can we do better than this? In the real world, there are examples. So people reuse code a lot. This simple is-out package, you can see it's been being downloaded weekly for 400,000 times, so that's quite a lot. However, testing techniques are not really usable for certain applications. The Z3 SMT solver, for instance, which is heavily used in academia and in other projects, is clocking in at just above 500,000 lines of code. Applying testing techniques to that is very infeasible, just due to the sheer size, not to mention the domain in which the tool works, that of SMT solvers, which itself is a very difficult domain. And finally, fuzzing is a useful technique. And by fuzzing, I mean, if we produce some random input, or random testing rather, is a useful technique. But then the problem is the Oracle problem. For some random input that we can generate for our given SUT, how do we know what the output is supposed to be such that we can identify errors in the SUT? In order to tackle all of these issues, there is metamorphic testing. Here is some background. Suppose we have some input I to our SUT represented by function f to obtain f of I. Suppose we can generate some alternative input I prime using some relation R, which we'll know exactly when the domain comes what relation R represents, but there's just some relation R between the two. If that I prime is compatible, a valid input to our SUT, then we obviously apply our input over it. And then we could potentially observe some relation S over the two respective outputs. And we can say that RS is a metamorphic relation if R holding over I and I prime implies that S holds over f of I and f of I prime in this case. Of course, when we go to the practical domain, we replace RF with our SUT. How do we actually identify these R's and S's? And in the case of an SUT as complex as Z3, how do we even begin to think, even if we practically apply the SUT over some input, to look at the output and understand how they relate, and then corroborate that with the relation over the inputs? So it's much more complex in practice to apply this, and this is presumably why metamorphic testing has not seen a good uptake practically in the actual domain in engineering. Therefore, what we propose is a slight alteration of metamorphic testing, which we call metamorphic testing with high-level operations. Instead, we have a singular input, and and then we have two syntactically distinct but semantically equivalent applications of some internal operation, in this case represented by f and f prime. And because f and f prime are semantically equivalent, we expect the outputs to be equivalent themselves. For a, for a concrete, there are three components of metamorphic testing with high-level operations. One thing is the variance, which is the end result that must be equivalent. So as I showed before, the outputs that must be equivalent. In this case, this R0 and R2 are expected to be equivalent after the application of those operations. Then there are these inputs represented here by out8, out16, and out28, which we can see are used throughout the generation of the variance. And then finally, the check based on the the semantic operation itself. In this case, a simple equality check and simple equality check. In addition to these components, we also apply composition of metamorphic relations. So if we have some input and we have a pair of MRs f and f prime, we can apply an f and f prime to obtain f of I and f prime of I. And then if if those outputs are valid inputs to a subsequent pair of metamorphic relations, we can then apply that pair here represented by G and G prime, and so on and so forth, as long as we basically create this chain of application metamorphic relations to create a more complex input to exercise more of the SUT. So here, for example, if we start from this triple of input of variables, then we apply commutativity of addition, which is a metamorphic relation in our case. Say on the top side we add out16 with out8, and on the bottom side we add out8 and out16. It is important to know that this operator plus is obviously plus is rather simple operator, but in the context of Z3, for instance, addition might not necessarily be as straightforward, and these out8 and out16 obviously might be very complicated types, and it is important to exercise even the trivial operations that we consider in our case. Going forward, we can get some more complex MRs. So for example, again, using mathematical identities, however, a to the power of n plus m is a to the power of n times a to the power of m. So as long as the SUT implements these operations, we can translate from the domain of integer arithmetic. For instance, we can translate to the domain of SMT formulas. And finally, we just check by construction, these steps, we semantically know that they should produce equal outputs. So our check then becomes equality over the resulting variables. In addition to composition, to make even more complex inputs to the SUT, we do something called recursion. So the third step is not a direct application of a pair of metamorphic relations, but is produced by recursion. So we can see on the right-hand side, on the left-hand side, we have a 0, but on the right-hand side is a more complex expression. But if we go into the details, out8 plus 0 is out8, out8 to the power of 1 is out8 again, and then obviously out8 minus itself is 0. And we can see that these are equivalent. But what we do here is inversely apply some metamorphic relations. So if, for example, an identity relation, out8 plus 0 is expected to be an out8. So we can use this to, yeah, another way to make more complex inputs to our SUT. We implemented this idea in a tool called MF++. So we expect the user to provide a template file which represents the skeleton and performs any sort of setup the SUT might require. For example, initializing a context or preparing some stuff. And then a library specification, which should represent these distinct syntactic implementations of semantic operations, and also implement the checks to be made by the tool. Both of these were provided ingredients are written in C++ source code. At the moment, this is a tool for C++ libraries. Then MF++ takes these and essentially generates a random test by creating this whole sequence of metamorphic equivalent variants, and also checking the user provided checks over them and flags up any issues that might arise. We have evaluated the tool and our technique over a total of 6 C++ libraries, 2 of them in the domain of Presburger arithmetic, namely ISL and libomega, and 4 of them in the domain of SMT solvers, namely Z3, CVC4, Yices2, and Bulecter. And we were able to identify a total of 21 bugs, I believe it is, out of which 18 have been reported and fixed, and 3 of them have subsequently been reported and confirmed. We also implement automated reduction in our toolchain because we have the template file, which is a skeleton of the eventual test case. We can, looking at the delta between the two, we can identify exactly those pieces of code that have been generated by MF++, and then limit reduction over those by essentially undoing what MF++ does at some way. But probably more crucially is that the test case itself contains an oracle by virtue of implementing metamorphic testing. And we know where that oracle is because we know how MF++ generates it. Therefore, we can maintain that oracle in the reduced test case, ensuring that the reduced test cases themselves perform some meaningful computation that can be checked. Some examples of automated reduction is sequence shortening. So for example, here we have R0 and R2 are obtained by a sequence of 3 operations. We can simply remove the middle operation, for example, so that they're both produced only by 2 equivalent operations. And recursion folding, as I showed the example of how we recursively generate D0 in R2, we can simply undo that recursion and know that we started from a 0 to obtain that, to again simplify this. In order to evaluate the automated reduction, we perform coverage reduction, which is an instance of cause reduction. We take, for an SUT, we take the test suite of the given SUT and compute the coverage attained by that respective test suite. And then we apply MF++ with handwritten user specifications, apply it for a number of hours to obtain the amount of coverage MF++ is able to achieve. And then we compute the amount of coverage MF++ is able to achieve that the suit is unable to achieve, the test suite of the SUT is unable to achieve. So that is the exclusive circle on the right-hand side. And using this, we were able to generate a total of 21 minimized test cases, which improve coverage over 3 of these tools, namely Z3, Yices2, and ISL. And they have been contributed to the test suites of these 3 tools after contacting the authors. And so it was a more involved process to ensure that these generated test cases are high quality, mostly having been automatically reduced and with a bit of manual modification to just make them be easily included in the test suites. For the future, we would like to expand the libraries and domains tested. We have been focusing on numerical domains, namely Presburger arithmetic and SMT solvers, but this idea should be generally applicable and also not only to C++, but any graphics libraries or compression libraries, system libraries, or any other languages. It's just for C++, it was extremely useful to have Clang, which allowed us to parse C++ source code and allow the users to provide C++ source code for the user required ingredients. There are improvements to be done at the reducer level. During the evaluation of the reducer, we identified further options, further opportunities for automating what can be removed. And that's also one thing. And of course, we could probably even go further in some aspects. And finally, connect to the developers to show them this is our tool that could potentially help you. And with the idea is that you have an initial work that you need to do to provide user ingredients, but then you essentially have an unlimited amount of tests that come from this initial work, and hopefully it will be useful to finding bugs in the future. Yeah, thank you very much. We are the tool is available on GitHub at the links, everything's over there if you'd like to see them. And if there are any questions, I'm happy to receive them right now.
Excellent. Thank